Good morning. Today we are going to discuss differential phase shift keying. Before going to differential phase shift keying, I forgotten yesterday the constellation diagram of BPSK. The constellation diagram of BPSK is constellation diagram of BPSK. Constellation diagram of BPSK, we know that when symbol 1 is transmitted, the modulated signal S1 of t is equal to A cos 2 pi fct. When symbol 0 is transmitted, the modulated signal S2 of t is equal to minus A cos 2 pi fct. Okay, this can be also be written as A cos 2 pi fct plus pi is equal to 0 degrees here, and here A cos 2 pi fct plus is pi, right? Okay, instead of A we placed that A is equal to under root 2p. For symbol 1 here I am writing root 2p cos 2 pi fct for phase shift of 0 degrees. For symbol 0 it becomes minus or root 2p cos 2 pi fct plus pi. The constellation diagram is okay. This is, for example, it is cos 2 pi fct, 180 degrees of cos 2 pi fct minus cos 2 pi fct, right? Okay. So when you will get cos 2 pi fct for 0 degree, for bit 1 phase shift is 0, you will get cos 2 pi fct, right? So this is bit 0. The value is here root 2p cos 2 pi fct. Now here at bit, this is a 0 degree phase shift, and for bit 1, okay, this is 0 degree phase shift. For bit 0, the phase shift is 180 degrees, so it becomes what? Minus cos 2 pi fct. Yes or no? It becomes minus root 2p cos 2 pi fct. This is bit 0. This is the constellation diagram. Its value is here minus root 2p cos 2 pi fct. Okay, remember this one. Yesterday I forgotten the constellation diagram of BPSK. Now today we are going to discuss the topic is differential phase shift keying. DPSK is also called as differential binary phase shift keying. Differential binary phase shift keying. So here already we have BPSK. Why we are going to use DPSK? So the DPSK is non-coherent version. Non-coherent version of BPSK. Okay. So here at the receiver side need not to use carrier signal. Receiver side we are not required carrier signal. So carrier signal is not required. So the meaning of that one, between transmitter and receiver, phase synchronization is not required. So we can simply call it as between transmitter and receiver synchronization is not required. Okay. Now the differential BPSK, it is a non-coherent version of BPSK. The block diagram of differential BPSK or that can be achieved by a differential encoder followed by binary phase shift keying, we will get DPSK. The block diagram of DPSK is, first part is the differential encoder. So the differential encoder, it consisting of X NOR gate with delayed by TB. Another input is delayed by TB. Input is a binary sequence. Output of my differential encoder, I am call it as DL. The delayed by version is called as DL minus 1. Here input sequence I am call it as BL. Okay. So this part is followed by BPSK modulator. We know that BPSK modulator consisting of polar NRZ followed by multiplier with carrier signal A cos 2 pi FCT, and here you will get BPSK output, but in this case you will get DPSK. Okay. Now see here, this part is differential encoder. This part from polar NRZ, from this part is called as, up to this part is called as BPSK. So differential encoder is followed by BPSK, you will get DPSK. Now let us take one example to understand the operation of DPSK. Here we are going to discuss DPSK modulation and demodulation, right? So it is modulation, I am going to discuss here, modulation part. In the modulation we are using A cos 2 pi FCT, this is a transmitter side, but we are not using carrier at the receiver side, please remember that. Now for example, if you take input binary sequence BL, input binary sequence BL is equal to 0 1 0 1 1. This is my input binary sequence. We know that the operation of XNOR operation is AB is input XNOR. If inputs are 0 0 0 1 1 0 1 1, if both the inputs are same, output is 1. If both the inputs are same, output is 1. If the inputs are different, output is 0. Please remember that. This is a XNOR operation, not XR. Now see here, first bit, the binary sequence is given to differential encoder. The differential encoder consisting of XNOR gate with delayed by TB. Now first here I want to write input binary sequence BL. Input binary sequence BL is, first bit 0 is transmitted at TB duration, second bit 1, 0 1 1. Every TB duration only one bit is transmitted. Why? Because it is a differential binary phase shift keying. Okay, because of binary, only at a time for TB duration we can transmit only one single bit. This is my input binary sequence, that is BL. This is BL. Next, to perform operation of this one, yes, that is a delayed by TB we required, delayed by TB signal. So, to perform operation I am taking here DL. Output of differential encoder, that is DL. To perform XNOR operation we required initially one bit. Here already one bit is giving. So, to perform operation it is connected, it is a feedback is connected to this one. So, we required one initial bit. So, that initial bit I am taking as 0 or 1. This is my initial bit. Now, this is, that is a delayed, this is this only one point, this is called as DL minus 1, this only one bit is DL minus 1 here. Okay. Now, the DL output, DL minus 1 is given as well as BL is given, the DL output is first bit, the DL output by performing XNOR operation 1 0, 1 0 output is 0. So, inputs are different. So, output is 0. Again 0 1, output is 0. Again 0 0, same inputs, output is 1. Again 1 1, same input, output is 1. Again 1 1, same input, output is 1. This is my differential encoder output. Differential encoder output. This differential encoder output is given to polar NRZ. We know that. So, wherever the 1 in polar NRZ, we know that 1 will be mapped to plus A volts or plus 1 volt polar NRZ, and 0 will be mapped to minus A volts or minus 1 volt, right. So, after performing that one, that plus 1 and minus 1 is multiplied with A cos 2 pi FCT, you will get minus 1 minus A cos 2 pi FCT and plus A cos 2 pi FCT depending on ones and zeros, right. So, you will get a differential phase shift keying. Now, here I am not drawing that entire figure, please here see here. We know that for 1 the phase shift is 0 degrees. For 0 the phase shift is 180 degrees, yesterday only we discussed, right. So, here just I am writing the DPSK, the transmitted signal or modulated signal, or transmitted signal phase. So, I am not drawing the signal here, just I am writing the phase, what phase for single bit is while transmitting. So, we know that bit 1 phase shift is 0 degrees, bit 0 phase shift is 180 degrees. So, here this is a transmitted signal, bit 1 is phase shift is 0 degrees, yes, bit 0 is a pi, bit 1 is a 0 degrees phase shift, okay. Bit 0 is pi again, bit 1 0 degrees, bit 1 0 degrees, bit 1 is 0 degrees. This is the transmitted phase shift of DPSK, right, and this signal is transmitted. Now, the receiver will be received the signal. So, this signal is transmitted through the channel, and receiver here, receiver will receive the same phase shift, same DPSK signal. So, here 0 pi 0 0 0, the receiver will receive the same phase shift, okay. Up to this one I hope you are clear the concept, okay. Now, I am going to discuss the detection of DPSK. The detection of DPSK, it consisting of DPSK detection. DPSK detection. So, detection of DPSK, it consisting of the block diagram is modulated signal is DPSK signal. That signal directly given to one multiplier and delayed DPSK signal. By TB signal is also given to multiplier. Output of this multiplier is given to low pass filter, or it is also called as an integrator, and followed by decision device. Decision device, internally it consisting of threshold voltage level 0. Here you will get demodulated signal. Okay. Now see here, first we can assume the DPSK first bit is transmitted. The first bit is, let us assume 1, its phase shift is 0 degrees. The delayed bit is also transmitted, that is also bit 1, its phase shift also 0. So, because of phase shift is 0, we will get the signal that is A cos 2 pi FCT. Here also the delayed bit is also bit 1, its phase shift is, again here the signal we will get A cos 2 pi FCT. Yes or no? Just now I said here. See here, for 1 is mapped to plus A volts or plus 1 volt, the phase shift is 0, right. So, here 1 is multiplied with A cos 2 pi FCT, you will get A cos 2 pi FCT. For 0, you will get minus A cos 2 pi FCT. Okay. Now, here I am writing the case 1. Case 1, okay, both inputs, that is DPSK and delayed TB value, both inputs are same. Now see here, if both inputs are same, what happen? So this is A cos 2 pi FCT, A cos 2 pi FCT. Both A cos 2 pi FCTs is given to multiplier. So output of multiplier is A square cos 2 pi FCT. This output of multiplier is given to low pass filter or integrator. So next one, integrator output. So this output of multiplier is this one. I am solving this one, A square, this can be written as 1 plus cos 2 pi 2 FCT by 2, right. Now this can be written as A square by 2 plus A square by 2 cos 2 pi 2 FCT. Now this can be passing through low pass filter. Here the low pass filter allows only low frequency term and it rejects high frequency term, right. So in this case, this is my high frequency term, it is the low frequency term, right. So here low pass filter output is, this one is rejected, only here I am getting A square by 2. This is for symbol 1, that is 0 degree phase shift. If both inputs are symbol 1 and 0 degree phase shift. Case 2 is as inputs are different. Inputs are different means, see here, Here the bit 1 is received here. The delayed bit I am assuming the case 2, second case I am assuming the delayed bit is 0, so that phase shift is 180 degrees. Here I am getting minus a cos 2 pi fct. Please remember, this brown color is case 1. The case second one is here input is bit 1 with 0 degrees phase shift. The equation is a cos 2 pi fct. Bit 0 and it is a 180 degrees phase shift. The equation is minus a cos 2 pi fct. This two signal is given to multiplier. So here this two signals is given to multiplier. I am getting a multiplied version, that is output of multiplier. Output of multiplier is, see here, a cos 2 pi fct into minus a cos 2 pi fct. So it becomes minus a square cos square 2 pi 2 fct 2 pi fct, right. Now again I am writing here this one, this can be written as a square by 2 1 plus cos 2 pi 2 fct, right. This is also passing through low pass filter. Here I am getting output of low pass filter is minus a square by 2, right. Now so these two inputs, these two outputs of low pass filter, this is a case 1 output, and this is a case 2 output. So this case 1 output as well as case 2 output is passing through decision device, right. So here for case 1, see here, case 1 output is a square by 2. This a square by 2 is compared with decision device internal voltage, that is V threshold voltage 0, right. So a square by 2 is it is a greater value than 0, so that decision device will produce output in the favor of bit 1. The decision device produce output in the favor of bit 1. Similarly here it is minus a square by 2, so it is compared with 0, this value is less than 0, so that my decision device will produce the output in favor of bit 0. The decision device, this value is less than 0, it produces output, that is bit 0. So here I am concluding here what I am doing. If the both the inputs, means both the inputs are same, output bit is 1. If the both the inputs are, if the inputs are different in receiver, so output is bit 0. The same I am applying here. Just now we are done. See here. So this signal is received by the receiver. So I am designing at the receiver the device it takes. If the both the inputs are same, the device, if the both the inputs are same, it produces a output, that is 1. If the both the phase differences are different, it produces output is 0. See here, I am comparing these two phases. The phase difference is different. The phase difference is difference means here, that is produces bit 0. If the phase differences are same, it produces bit 1. Phase differences are different, produces bit 0. The phase differences are same, produces bit 1. The phase differences are same, the produces bit 1. If you compare this V signal and input binary sequence signal, these two are same, right. So at the receiver end I am producing same output, which is same as input binary sequence, right. So what I am done at the receiver, so I am at the receiver, I have made a device, that device will produce, if the input phase differences are different, it produces a output, that is bit 0. If the phase differences are same, it produces a output that is 1. So, this is the operation of DPSK detector, clear? This is the operation of DPSK detector. Now, I hope you will get, you may get this entire operation of DPSK. Now, what is the advantages and disadvantages of this one? Just I will mention only 2 advantages and disadvantages. The first advantage is, see here at the receiver side we are not using any extra carrier, that means we are not using any local oscillator. Because of that one, the complexity will be reduced, synchronization is not required, right. So, that the cost of the device will be reduced. Okay. And another one, the disadvantage is it consisting of noisy, it consisting of little bit noisy, that is a disadvantage. Okay. Now, see here, please try to draw the waveforms of signal. Okay. So, this is a binary sequence, input binary sequence, after that this is a DL. So, from here to first one binary sequence, just within 5 minutes I will conclude that waveforms of DPSK. Please concentrate here. Okay. Input binary sequence is binary sequence, that is BL is 1 0 1 1. This is my input binary sequence 0 1 0 1 1. This is BL, right. For DL value initially I am taken 1, because of performing here 0 0, right, 1 1 1. Okay, this is my DL. Now, this signal, this differential encoder, this is differential encoder output is passing through polar NRZ. So, polar NRZ signal waveform, polar NRZ waveform at the time t, TB, 2 TB, 3 TB, 4 TB, 5 TB, 6 TB. Here voltage level, that is plus 1 volt, minus 1 volt. Okay. This is the polar NRZ, yes or no? This is the polar NRZ, polar NRZ. The polar NRZ, because of symbol 1, first bit is symbol 1. So, second bits 0 0, next 3 bits 1 1 1 2 1 1, right. This is polar NRZ. This signal is multiplied with what? Carrier signal, yes or no? This signal is multiplied with high frequency carrier signal with T. Same carrier signal, just roughly drawing carrier signal. This is my carrier signal, and this carrier signal now, what is the definition of BPSK? The pace of the carrier signal is varied according to input data, that is called BPSK, right. So, see here, first bit is 1, here I am drawing the signal, bit is 1, here the DPSK output, TB, 2 TB, 3 TB, 4 TB, 5 TB, 6 TB. First bit DPSK output, here same signal I am getting here. The transition, it changing from 1 to 0, phase shift, plus 1 volt, here minus 1 volt, phase shift, 180 degrees phase shift. Again there is a no phase shift from here to here up to 3 dB, the signal will be continuous. Now, at 3 to 4 TB, it is changing from minus 1 to plus 1. So, it takes the phase shift here, 180 degrees, and again there is no phase shift, the signal will be continuous, right. If you see here where you find the phase shifts, see it is changing from 1 to -1 means first bit is 1, this is up to this one 1, so that is 0 degrees phase shift. It is changing from -1 to 1, this is a 180 degrees phase shift, so here for second bit you will get 180 degrees. So there is a no phase shift means same phase shift will be available, right. Again from 3 TB to 4 TB the phase shift is occur, that is here -1 to +1, that is 0 degrees phase shift. From here to here there is no phase shift, so sorry, this is a 0 degrees phase shift, 0 degrees phase shift, 0 degrees, these are the phase shifts, 0 degrees phase shift. This is my modulated signal, and due to this one I am getting a demodulated signal. That demodulated signal is, how we will get demodulation signal? By comparing the two phase shifts, it produces bit 0. By comparing two phase shifts, it produces bit 1. Here because the phases are same, phases are different, 0, phases are same, yes 1, the phases are same, 1, right. So this is my input binary sequence which is same as input sequence, right. Now today I am giving assignment. Right, first one, what is DPSK? What is DPSK? And DPSK modulation and demodulation. With diagrams. And waveforms. Next, applications or advantages. Advantages and disadvantages. Okay, thank you. I hope you will clear the concept of DPSK.